Hi guys, welcome to the lesson of partial differential equations. So we are discussing formation of partial differential equations by eliminating arbitrary constants and arbitrary functions. So on the same topic we did some examples in the previous class. So now we will take some more examples so in which the arbitrary function is basically the function of two integral curves, because in the last class we did solve a question where it was a function of only one integral curve. It was like f of x squared minus y squared. So this was only the one integral curve. So now we will have a function of two integral curves. So let's start. Let's say that we have a function that is phi is equals to function of x over y comma z over x. So now we want to find the partial differential equation which is formed by these two integral curves, or basically we can say that these integral curves are the solution of some partial differential equation. So we have to find that specific partial differential equation. So the first step is to suppose u is equals to x over y and v is equals to z over x. If you guys remember in the previous lectures, when we solved PDEs basically of this form, dx over p is equals to dy over q is equals to dz over r. So by solving these we get some functions, some integral curves, and at last we write the integral curves like this. Say x over y is equals to c1 in this case, and z over x is equals to c2. So now I can follow the same procedure, and I assume that u is equals to xy and v is equals to u is equals to x over y and v is equals to z over x. Now what we have to do is we have to solve this determinant. Basically this is also called the Jacobian, and we will equate it to 0 to find the partial differential equation. So let's start. So we have to find ux. What does it mean? It means that we have to differentiate this u with respect to x partially. So it's dawa x over dawa x, so it will be 1 over y. This implies that ux is equals to 1 over y. We can box this function, and now we will find vx. So vx will be equals to dawa over dawa x multiplied by z over x. So now this function will be differentiated using the division rule. So we'll apply the division rule. It's x times dawa z over dawa x, because this z is the dependent variable, and minus z times dawa over dawa x multiplied by x divided by x squared. So we will get xp, because we can write p in place of this, and minus z over x squared, because this the partial differential of this x will be 1, so we will get xp minus z over x squared, which is basically equals to vx. So we found ux and vx, and the next step is to find uy and vy. So Similarly, uy will be equals to dawa over dawa y multiplied by the function u, that is x over y, and this will be nothing but x over y squared, negative x over y squared, because when we will differentiate this function with respect to y, we will we only have to differentiate y, because this x is another independent variable. And now we will find vy. So vy is again dawa over dawa y multiplied by z over x. So we'll treat this x as a constant, so I can write it as 1 over x, and then dawa z over dawa y, this is dawa z over dawa y, which I can also write as q. So this is our vy. Now we have found the vx vx ux and vy uy. Now we will find the determinant. Ux is 1 over y, and then vx is xp minus z over x squared, and then uy is negative x over y squared, and then vy is q over x, and this is equals to 0. So we will multiply this for determinant, so it will be q divided by xy minus this negative x over y squared times xp over x squared, then minus and minus will plus xz divided by x squared y squared, and this is equals to 0. So we'll simplify this, we will get q over xy minus 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 plus, this will be plus, then this x squared will be cancelled by these x's, so we will left with the p over y squared, this x will be cancelled by this, and we will left with negative z over x y squared is equals to 0. So now we can take some LCM, the least common multiples, and we can simplify this function. So let's do in the next step. So the LCM will be xy squared, so we have to multiply this by y plus multiply this by x, and this will be negative z divided by x y squared is equals to 0. So xp plus qy is equals to z, and we can also write it as x zx plus y zy is equals to z, and also we can write it as x dawa z over dawa x plus y dawa z over dawa y is equals to z. So these are some common notations of representing the partial differential equations. So now we see that the function that was initially given, it was let me look at the question. It was x over y comma z over x. So this function is basically is equals to 0, we can say is equal to 0 or 5. So this function is basically the integral curves. These are the integral curves of this partial differential equation, and we can verify it by again solving it like this dx over x plus equals to dy over y is equals to dz over z. So we can verify this by solving these differential equations, by transforming this into the system of differential equations and then solving it. We will again get to the conclusion, and we will see that we find these two curves. Okay, let us take another example. So in order to make things more perfect,